guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. One thing I wanted to point out is that both enthalpy and entropy, make sure you don't confuse them, are state functions. And like a standard enthalpy value, we can talk about standard entropy values. So remember we talked about delta H naught, and if it has this 0 right here, it's a standard enthalpy value. We can also have the same thing for standard entropy values. And this is when it's at 298 Kelvin and 1 atmosphere. We can use these values to calculate the delta S of the reaction, just like we did for enthalpy. So I'm going to go over this very briefly because it's the same exact reaction for what we did for the enthalpy values. So the delta S of the reaction is equal to the sum of the individual standard entropy value of the products minus the sum of the standard entropy values of the reactants. Remember, entropy is also an extensive property, so you're going to need the number of moles before each of the products and reactants. So make sure whenever you write out whatever equation you have that you balance out the number of moles, because you always want to include the number of moles for the products and reactants when doing this equation. More complex molecules have higher standard entropy values due to a greater number of vibrational and rotational motions. So basically, atoms have a greater number of possible positions when they're more complex. So now I wanted to relate phase changes, which we've already talked about, with entropy changes. So if you go from a solid to a liquid to a gas, as you would expect, there's a change in the entropy value. I mentioned this very briefly before because gases have more areas in which the energy can be distributed compared to a solid, right? This is when we talked about the Boltzmann's constant and the Boltzmann's equation. Okay, well, this also makes sense because if you think about water as a liquid, this can occupy many more positions than water as a solid, right? In the form of ice. The entropy change of melting ice is given the equation Q rev over T, which I showed you before is the second law of thermodynamics, and it can be written as the delta H of fusion over temperature. Now this temperature has Tm because this is called the melting point temperature. And the delta H of fusion is the heat required to melt 1 mole of ice to water at constant pressure. So this constant pressure part is really important because this is what allows us to equate the Q, which is heat, to delta H of fusion. Remember that we looked at that relationship before where we said delta H equals Q at constant pressure. So another thing we can look at is the delta S of boiling. So now we're going from a liquid to a gas, right? And so now we can write this out as Q rev over T, but then instead of the reversible heat, call this delta H of vaporization, or VAP, and over TB, which is representative of the boiling point. And so, as you can see here, the delta S of fusion is from going from a solid to a liquid. The delta S of vaporization is going from a liquid to a gas. The magnitude of this delta S value depends on the temperature at which heat is being transferred. So the delta H of reaction plays a really important role at low temperatures. So we've been talking a lot about the system or the reaction itself, but I wanted to briefly talk about what's happening in the surroundings. So at constant temperature, an exothermic process in the system causes heat flow into the surroundings, right? And so the system loses heat, which can be written as the delta S of the system, which is Q reversible over T, is going to be negative because it loses heat. On the other hand, in this case, the surroundings gain heat. So the delta S of the surroundings is equal to the reversible heat over temperature, and it's going to be positive. So as you can see, the sign of delta S depends on the direction of heat flow. So if talking about delta H, or enthalpy of a system, then in terms of the surroundings, we can write it out as delta S of the surroundings equals negative delta H of the system over T. For example, in an exothermic reaction, delta H is going to be negative, right? Because it's exothermic, and in that case, the delta S of the surroundings is going to be positive, which is what we just showed for an exothermic process. And this must be since heat flowed into the surroundings from the system. And so here are some other equations that you should remember when talking about the system and surroundings. The delta S of the universe is the delta S of the system plus the delta S of the surroundings. So remember, it's a state function, so you can add the values together. Also, the delta S of the universe is always positive for a spontaneous process, and that's something we learned from the second law of thermodynamics. And finally, the delta S of the universe is equal to 0 for a system at equilibrium. So these are a few relationships that will really help you. So try to remember those early on in this quarter.